All right, so we're going back to, well, not going back. We're done with probability now. So now we're moving on to a different part of the course, which is on matrices. Okay, so this is in chapter 2 of the textbook. And specifically, we're going to start today with 2.1, which is systems. It's on systems of linear equations. Okay, so first of all, let me try to explain what a linear equation is. So, example, if I take, let's say, 3x plus 2y minus 5z equals 12. Okay. So this is an example of a linear equation. In 3 variables. So my variables are x, y, and z. Okay. So it's an equation because it has an equals, right? An equation should have an equal sign in it. The reason it's linear is because, so linear means that all variables have exponent 1. So for instance, you have like x squared, or z, square root of z, or anything like that. Okay, and also your variables are multiplying to each other. So there's also no, x times y or anything, right? You've just got simple variables with coefficients, and all the variables have exponent 1. Okay, and you're not multiplying variables by each other. Right, so just anything that looks like, something times one variable, something times another, added up, and then equal to maybe some other number, right? Okay, so as an example, well, another example so x minus, let's say 3y equal to 6 is a linear equation in 2 variables. Okay. And so what we're really interested in is finding solutions to linear equations. So a solution is a choice for x and y such that the equation is satisfied. So I'll just say that the equation holds. Meaning that when I say the equation holds, I mean when you plug in that value of x and y, the left-hand side equals the right-hand side. Right? Can anyone see how many solutions there are to this equation? Yeah. So for this equation, there are infinitely many solutions, right? because no matter what I put in, if I plug in a value for x, no matter what it is, I can always find a value for y. So, and there's infinitely many ways to put in a value for x, and so there's infinitely many solutions. Okay, and there's you can graph the solutions if you wanted to, right? And that kind of when you graph them, then you'll see why these are called linear equations, because if you graph the solutions, they form a line, right? So just kind of a bit of a review. If I was to graph the solutions, if I solve for y here, I've got that y is 1/3 x minus 2, I think. Right? So this is the kind of slope in the y-intercept, right? So if I graph this, so I know that it goes through the point 0, -2. And for example, 6, 0, right? So it's a slope, a line of slope 1/3 that just kind of goes like this, right? It's supposed to be straight, but I'm not that good at drawing a straight line. All right, so this stuff should hopefully be familiar from high school. Okay, so like this line, these are the solutions to x minus 3y equals 6. Any questions about that? So okay, so this is just, all we're talking about so far is linear equations. Well, we need to also talk about systems of linear equations. So the idea there is we're going to have several linear equations, and we want to solve all of them simultaneously. So we want to solve systems of linear equations like, for example, if I take, so I'll just take this original equation, x minus 3y equals 6, and then I'll add another equation, 2x plus y equals 5. Sorry, 2x plus y equals 5. Okay, so this is a system of linear equations. I'll often just write SLE because it's a lot faster, but SLE stands for system linear equations. Okay, so a system of linear equations is just like a list of equations, right? Okay, and a solution is a choice of x and y that satisfying both equations. Okay. Now, let's kind of think of this, again, let's go back to this picture and think of this kind of geometrically at the start. So I've already plotted the line corresponding to these solutions. I'm going to plot the line for those solutions. So this line is the same as y equals -2x plus 5. So I don't know, I think hopefully this is kind of bringing back memories of grade 10 or grade 11 math or something, right, where you're plotting these lines. right? So this has y-intercept is 5, the slope is -2, so I should do this, that, and so on. Okay. So as long as I plotted these correctly, this is the unique point where they meet, right? So this is the point 3, -1. Right? So if I want, so this line is the solutions to the first equation, this line is all the solutions to the second equation. So if I want to satisfy both equations simultaneously, I have to pick a point that's on both lines, and there's only one such point. So here the unique solution is the point is when x is 3 and y is -1, right? Okay, and if you plug in these values into the equations, you can see that both of them are satisfied, right? So that would be your solution. Any questions about that? Yeah?
What's SLE?
Oh, system of linear equations. So it's just a short way of saying this. Any other questions? Okay, so drawing a graph like this is one way you can sometimes get a solution, but I wouldn't recommend this in general, right? Because so this worked really well when we had two variables, because we just have x and y, and we can just draw it on a board, right? There's only 2 dimensions. But we're going to be dealing with systems of linear equations that sometimes have 3 variables, or 4 variables, or 5 variables. And now you're talking about trying to draw in 3 dimensions, 4 dimensions, 5 dimensions, and kind of good luck trying to do that. Okay, so just drawing the picture and trying to figure out the intersection, that's not really going to work. So we want to come up with a systematic way of solving systems of equations without having to draw the picture. Okay, let's do an example, and then I'll introduce the method through that example. So concert has 2 different ticket prices. Okay, so there's one price for adults. And there's another price for children. Right, so what I mean by this is there's an adult price, a child price, so there's 2 different prices. So one group of people, so one group of 3 adults and 7 children pays $119. Okay. So let's say we don't know what the prices actually are, but we're just watching people buy tickets. We notice, 3 adults and 7 children, they paid $119. Another group of 5 adults and 5 children paid $126. Okay. And so the question is, what is the ticket price? What are the ticket prices? Okay. Okay. Was the question clear? So okay, so here I think it's kind of clear we've got 2 unknowns, right? We need to know the adult price and the child price. Okay, so I'm going to come up with 2 variables, x and y. So let's say x is the adult price, and y is the child price. Okay. So from this question, can anyone tell me some equation, some linear equation I can write down about x and y? Yeah?
X plus 7y equals 19.
Yep. Right, because we know 3 adults, so 3 times the adult price plus 7 times the child price. Those people paid $119, so this should equal 119, right? And then similarly, we've got 5 times the adult price, 5 times the child price, and that should be 126. Okay, and our goal is to determine x and y. Okay, so you might have seen like a lot of ways to do this, I don't know, in high school or something. But like, for example, solving for a variable in one of them, substituting into the other, etc. I would kind of suggest to you to try to unlearn most of those different ways. Well, okay, don't unlearn them forever, but for the purposes of this course, there's only going to be one method that we're going to use. So the only method, I'm pretty sure this is the only method we ever use. The only method we use in this course is something called Gauss-Jordan elimination. Okay, so, and I'm pretty sure most of your tests and stuff, they'll say, you know, solve this using Gauss-Jordan elimination. So if you use another method, you're going to lose some marks. So I really suggest learning this method. So let me try to explain what the method is, and then we'll solve this problem. So the goal of Gauss-Jordan elimination, okay, is to take your system of equations and transform it. So transform your system of linear equations into a very, very simple equation or system, which just looks like x equals something y equals something else, maybe. So what I mean by that, like we start with this equation that has x's and y's, these equations that have x's and y's all mixed together. And I want to step by step manipulate this until it just looks like x equals something, y equals something, right? Or I should say something prime or something, but different something. So when you do Gauss-Jordan, so there's kind of 3 steps you're allowed to do. 3 different things you're allowed to do. So one thing you're allowed to do is switch to equations. This seems like a silly one, but so all I mean is you've got 2 equations, one on the top, one on the bottom, let's say. You're allowed to switch them. So take the one on the bottom, put it on the top, take the one on the top, put it on the bottom. It doesn't really change anything, right? But you're allowed to do it. You're also allowed to multiply an equation and so you have to do this on both sides, right? Of the equal sign by a non-zero number, right? So if I've got an equation, I can replace that with 2 times that equation, or 3 times that equation, or 1/2 of that equation. Or I can take an equation and just multiply it by something. And third, I can add a multiple of one equation to another one. So I can take my first equation and I can add like 2 times the second equation or something like that. Let's see how this works in an example. So let's go back to this example here. Let me write this a bit smaller. So. Okay, so what I want to do is like, I want to apply these rules, these types of rules, and try to make this system of equations look more like this type, that is just x equals something, y equals something. Okay, there's lots of different ways you can do this. What I'm going to do is I'm going to start by saying, I'm going to take the second equation and divide it by 5. Right, because then I've just got the x with a coefficient of 1. It's going to be useful. So I'm going to write this by saying, I'm going to multiply equation 2 by 1 over 5. So if I do that, I've got 3x plus 7y is 119 again. And I've got x plus y is equal to 126 over 5. Okay. Doesn't look that much closer to the end, but yeah, let's see what happens. Okay. So right now what I'm doing is I'm sort of focusing, so I should try to give you an idea of where I'm trying to go with this. I'm focusing on the first variable here, trying to make the first variable well, I'm trying to get, at the end of the day, I want the first variable to just appear on one of the equations and not the other one, okay? So what I can do here to eliminate that variable from this equation, I can take equation 1, okay? If I want to eliminate the variable x, I can subtract 3 of these from it to get rid of the x. So I'm going to take equation 1 minus 3 times equation 2. Right? And if I do that, that'll completely eliminate the x's from this equation. Okay. So, right, so here I've got kind of 0x here. If I take away 3 times y, I'll have 4 y's. So I've got 4 y's equal to, so this will be 119 minus 3 times this, which you can do better than I can because I don't have a calculator up here. But this is 217 over 5. So that comes from just taking 19 minus 3 times this, right? Then my second row is the same. My second equation is the same. Okay. Now everything's getting a little bit cleaner, right? I pretty much know what y is at this point. So I can take this first equation, so I'll just continue here, and multiply it by a quarter. Right, if I take equation 1 and times it by 1 over 4, I've got y equals 217 over 20. Okay, and this one's like this. Is everybody with me on these steps so far? I kind of understand that this looks a bit messy actually. It probably looks even messier if you're writing it in your notebook, but we'll have a cleaner way of doing this in a minute using matrices. So anyway, just to finish this example, what I'm going to do, for whatever reason, I kind of want to do x equals something and then y equals something. So I kind of want to switch these. It's not super important to do that, but let's do it anyway. So I'll say I can switch equations 1 and 2. Which I'll write like this. I'm just swapping them just to get this one on the bottom, because that's what I said I was going to do, right? So x plus y is 126 over 5. Y is equal to 217 over 20. Okay, now I'm going to focus on this variable, the y, and I notice that it's pretty easy so now since there's no x here, it's pretty easy to just kill this y here, right? I can just, without changing the x at all. So if I subtract this equation from this one, this y is gone, right? So I'll take equation 1 and subtract equation 2. So I've got x equals whatever this minus this is, which is (287/20). That's what my first equation becomes, and then this one's just y equals 217/20, right? So I've got the right kind of format for my my answer. And then if you see what that actually is, it's 1435, so 14.35, and this one is 10.85. Right? If you go back to trying to remember what the question was about, this means the adult price is 1435, the child price is 1085. Right? Any questions about this? Might seem like a little bit of a convoluted method,
But yeah, I think it was just pretty good.
but it's actually gonna be quite a useful method when we deal with bigger systems, right? Okay. So yeah, to be honest, I think this is kind of hard to read. It's a little bit messy. Let's see a better way of doing it. So one kind of nice way of representing systems of linear equations, so SLE again, a system of linear equation, is with a matrix. Okay, so this equation where I had 3x plus 7y equals 119, and 5x plus 5y equals 126. So this system of equations you can rewrite in matrix form inside of this kind of box. So I write 3 for the coefficient of x in the first equation. So I just write 3, 7, 5, 5. Okay. And then I draw a line. So this line represents the equal symbol, right? So that these two equals. Then I write my 119 and my 126. Okay. And somehow it becomes a little bit nicer because you don't have to keep writing down your x's and y's. And somehow writing everything in a box like this kind of makes it, I don't know, it's easier to see on the page. There's no other good reason for it, to be honest. But it's just kind of useful. Okay. So you can represent your system of linear equations with a matrix. This is a matrix. And then basically these Gauss-Jordan rules, you apply them on the matrix. So when it says switch to equations, that corresponds to switching to rows. Of the matrix. Okay, so we can do the same kind of operations. Switching to equations becomes switching rows of the matrix. Multiplying an equation becomes multiply a row of the matrix. And the third thing you can do is add a multiple of one row to another one. Okay. And now our goal is, so there's no x's and y's anymore, right? We want to transform your matrix into one that looks like 1, 0, 0, 1, and then something here. And then whatever number is on the first row here, that'll be what x is equal to. The number on the other row will be what y is equal to, right? So hopefully it's clear that what I'm talking about here is exactly the same thing as with equations. Like there's no difference between matrices and equations. It's just different notation. Okay, so let's see how to solve this one again. But I'll do the whole thing thinking of it as a matrix. So I'll do the same thing. I'll look at my second row and I'll divide it by 5, right? Because I want to get a 1. Basically, there's a systematic way of doing this. Like your first step should be, look at your first column and try to get a 1 somewhere. Doesn't matter where, just try to get a 1, right? So I'm going to divide the first, I'll take the first row, sorry, the second row, and divide it by 5. I could have taken the first row and divided it by 3. No difference, right? Totally acceptable, either way. So this is 1, 1, 3, 7, 119, we have 126 over 5. Okay. So my first step is to get a 1 somewhere. And once I've got a 1 here, that 1 is really useful for kind of killing everything else in that column. So using that 1, I want to get a 0 everywhere else. Well, obviously this is only a two-row equation, so everywhere else just means the other one. But if you had like 5 rows, you want to kill all the other rows with this 1. So to get rid of a 3 using a 1, I take, I'm going to take, so the notation, by the way, you need to write this kind of notation for showing your steps. So what this means is, what I'm going to write here is, I take row 1, and I subtract 3 times row 2 from it. So that means I'm changing row 1 by subtracting 3 times row 2. Okay, and then I get a 0 here. Here, subtracting 3 ones will give you a 4. Then here, I again get 217 over 5 and 126 over 5 here. And I've got my 1 here. Okay. Now now I'm happy with my first column, right? It's got a 1, it's got a 0. Yeah. So 217 over 5 comes from 119 minus 3 times 126 over 5. So that's just taking this number minus 3 of those. Yeah. Okay, so now I'm happy with my first column. I want to work on the second column. And for that, I want to get a 1 somewhere, but not on the row. Like I've already got a 1 here, but that's not that useful for me. I kind of want to get rid of that 1. So I want to get a 1 in the other position. Because then I can use that to get rid of this 1, and then I'll pretty much have what I wanted here, except the rows are in the wrong order. I can switch them. So I'm going to take a quarter times row 1, which does this. Right? So this just means multiply row 1 by a quarter. Right? And now, okay, I'm trying to get 1, 0, 0, 1. So I'm going to just switch these because it looks kind of the wrong way around. So the notation for that is row 1 gets swapped with row 2. Okay. And now I've just got one more thing to do. I need to kill that 1. So just going to subtract that from it. So I take row 1 and I subtract row 2. Yeah, what was that again? Right, so again, this 287 over 20 just comes from 126 over 5 minus 217 over 20. Okay, so then your final answer would just be x is 287 over 20, which is 1435. And y is 217 over 20, which is 1085. Okay. Yeah.
What's the point of switching?
Nothing really. I mean, definitely in such a small example, if I had, so really the only reason is I'm trying to come up with exactly this form at the end. As you can see here, I'm not going to be able to get a 1 here, or I mean, the way it is, so I'm just trying to get, yeah, it's just to try to get it to look like 1, 0, 0, 1. But I understand what you're saying. If I was just here and I just get rid of that, it's pretty much the same thing, right? I don't really need to switch the rows. But that's only, like, when we're dealing with such a small example, it's kind of clear that you don't need to switch the rows, but when we deal with bigger examples, it'll be convenient to just, so like let's say we've got 5 equations. It'll be convenient to just get like 1, 0, 0, 0, 0, 1, 0, 0, or 4 equations, I guess. Somehow if these were all like mixed around, you might not be able to see what the answer is or something. I don't know. This is just how people want to. Typically you want to reduce it until it looks like, very simple. But there's no deep reason that you have to do it like that.
What are these operations called again?
Sorry?
What are these operations called again?
Elementary row operations. Yeah, oh, maybe I didn't write them. So these are called yeah, this general technique is called Gauss-Jordan elimination. These three operations are called the elementary row operations. So switching two rows, multiplying by a constant, adding a multiple one row to another, those are the three elementary row operations, and together they form this Gauss-Jordan elimination method. Right? So if you're asked something about elementary row operations, that's what it means. These three things. Yeah. Yeah, maybe that's a good reason for flipping them, to just make sure we know what's going on. So it's actually, yeah, it's not really row 1 that's X and row 2 that's Y. It's kind of the column 1. So that's a good question. Like, this column represents X, because those are the coefficients I had on X in the previous example. These are the coefficients of Y. So this represents X and this represents Y. However, if you don't flip things around to look like this, you might get confused, because you might think this row is corresponding to X and that row is corresponding to Y. If you get it like this at the end, it doesn't matter if you pick rows or columns. It's going to be correct either way. So, yeah.
So does the one kind of represent whatever variables, since there's 4 variables in that example?
Yeah. Yeah. Well, so the one, like 1 would just be like 1 times X in the first column. So yeah, these are kind of representing, there's kind of not 4 variables, but there's 2 equations and 2 variables. But yeah, you've got, this is like 3x, 7y, 5x, 5y. That's what it's representing. So 1 here is 1 times x, basically. Okay.